Okay, so I guess we should start. Well, thanks a lot everyone for joining us tonight. So we have a very interesting topic for our AIDA series. So the topic is geometric deep learning and several applications for multimedia. And it's a great pleasure to have here Hannes Fassold. He is very active in multimedia, has been one of the important stakeholders in the AI for Media project. He is very active in different publication in computer vision, multimedia, AI in general. He's been publishing a lot in ACM Multimedia, ICME, ICIP, and so on. So he coordinates a machine learning workflow and dedicated machine learning hardware and software infrastructure for the Digital Institute at GNM Research. And well, his research is quite well known, and I think the topic it's very very interesting. So Hannes, looking forward to your presentation.
Yeah, so thanks, Nico, for the introduction, and thanks to all who are attending this AIDA short lecture. So yeah, the topic is quite interesting. It's maybe a bit uh, more exotic than normal. Euclidean spaces where 95% of the machine learning is algorithms are processing. All right, so what's the motivation? So all these, or most of the classic neural networks, as you know, are restricted to data which is lying in vector spaces. But the thing is that data residing in non-Euclidean spaces is arising naturally in really many problem domains. And you have to sort of map them then artificially to Euclidean spaces. For example, a few examples for important non-Euclidean spaces. If you have like a panorama camera, a 360-degree camera, what you are capturing there is, in fact, of course, a spherical image. So you have the whole field of view, the 360-degree view. And in order to map that into the usual rectangular pixel representation, this sort of spherical image is usually projected via, there are different projections, but usually you're using a equirectangular projection, which brings itself a couple of issues I will present in the next slide. Or if you have 2D or 3D point meshes, you're having a sort of graph, an undirected graph. For example, if you get those as the triangulation of the point cloud. Or also if you're doing human pose estimation, so you're getting sort of a skeleton in 2D and 3D, and that's also naturally a graph, of course. Then you have all these kind of rigid body transformations. So a rigid body transformation, as you will know, is a rotation and then a translation. And these transformations are everywhere in 3D photogrammetry and kinematics, but their representation in a matrix is actually a sort of a manifold space or a Lie group. And then you have symmetric positive semi-definite matrices, which all arise also in a couple of applications as input data For example, in diffusion tensor imaging, you get those matrices. And they built also a non-Euclidean space. Okay, so what are now the benefits of keeping algorithms in sort of a non-Euclidean space? The main advantage is that you don't have to find an auxiliary mapping to or sort of artificial mapping to an Euclidean space. For example, as mentioned, for images from a 360 cameras, you usually have this mapping via the equirectangular projection. This artificial mapping complicates the algorithm workflow, and it usually leads to additional mathematical and numerical issues, and also sort of introduces a new issues with it. For example, when you're employing equirectangular projection, you have, I suppose you have seen those captured images already. You have distortion in the image in equirectangular projection, especially towards the upper and the lower border of the image, so towards the poles of the sort of spherical image. You have the border ambiguity because actually the pixels on the content on the right border is near is neighboring to the content on the left border. So you have introduced an artificial border actually, which complicates things like object detection and so on, of course. Um, and many research works really successfully employing non-Euclidean spaces. For example, the DeepMind GraphCast algorithm for weather forecast. It utilizes a graph neural network, and which is in sort of multiple sort of resolutions or scales. You can see that on the right side, and it makes like a 10-day weather forecast in less than in 1 minute. All right, so what is now geometric deep learning? That's deep learning with data lying in non-Euclidean spaces. So either on the input layer or on the intermediate layer or on the output layer. For example, yeah, on the input layer, you can have the input data as a graph or as a covariance matrix or a rigid body transformation matrix. Yeah, or you can have the input normally in a Euclidean space, but you have to add an intermediate layer in the network for things like a rigid body transformation, which is, as I mentioned, very useful for all sort of 3D computer, 3D photogrammetry problems. Or you have it on the output layer. So for example, if the output is sort of this spherical image. So geometric deep learning usually deals either with graphs or manifolds. So graphs, as all of you know, these are consisting of vertices and edges, and the manifolds are interested because they are sort of the natural generalization of a vector space, I would say. So they are really well suited for that. and they are quite easy to grasp. So the main property of a manifold is that it looks locally like a d-dimensional Euclidean space. The simplest manifold for sure is a sphere. So a sphere is a two-dimensional manifold. Also like the torus here at the right side is also a two-dimensional manifold because locally you can approximate it with a two-dimensional plane, of course. Yeah, and especially the Riemannian manifolds are very useful because they have the main advantage is that you have distances there. And in this introduction part, so the theoretical part, we will focus more on mainly on the Riemannian manifolds. Due to lack of time and because they are really interesting from a theoretical perspective. And then I have a block with applications of this geometric deep learning in multimedia, and there I will present a mix of also applications where graphs are employed. Yeah, so let's go a bit into manifolds and tangent space. So a manifold M of a certain dimension D is now a topological structure which locally, so in the neighborhood of a certain point P of the manifold, so locally it looks like a d-dimensional Euclidean space. And you can see that like in the right, you have this sphere, which is a two-dimensional manifold, as already said. And then in the neighborhood of this certain point P, of course, you can approximate it very well with by just fitting a tangent plane at this point. Yeah. So, which brings us to the important concept of a tangent space, TPM, located at a certain point P of the manifold. So this is, yeah, of course, the best local approximation of this immediate neighborhood of the point P with a d-dimensional Euclidean space. And yeah, can be seen as of course, as a linear approximation of these manifold M around this point P. And for a two-dimensional manifold like a sphere, the tangent space TPM corresponds, of course, to the tangent plane at the point P, which you can see at the right side in these two graphs. So I think that's quite easy to grasp. Now it gets a bit more involved. So the main advantages mentioned of this Riemannian manifold is that you can measure this, you have curves and distances on this manifold. So technically, the Riemannian manifold is a smooth manifold which is equipped with an inner project TP, and this inner project must exist on the tangent space TPM for each point P of the manifold. Yeah, so that's the sort of technical definition of this Riemannian manifold. And as usually, and as you will know from linear algebra, an inner product G induces always a norm on the corresponding vector space or inner product space. And That's the same here. So this inner product induces a norm, but not on the manifold, of course, but on the tangent space at each point. And this allows us now to calculate curve lengths. And later from the curve lengths, we can calculate distances on this manifold. So we have now these curves, CT on this manifold. So T is here the time, and the curve is starting at a certain point, and then you're moving over this manifold. And on such a Riemann manifold, you can calculate now the length of this curve, CT, just by integrating the norm along the curve. Yeah. Of course, this is very high level, yeah, because I can't bring all the details. But that's the basic idea. So now you have a curve length, and the next step, of course, is then you can define the concept of a geodesic. And a geodesic for 2 points of the manifold P and Q is now defined as the length minimizing curve which is connecting these 2 points. Yeah, and you can see that on the right side, and it maps on the sphere. It has a very intuitive explanation. You can see this geodesic here on the right side on the sphere between P and Q. And from the geodesic, we can now introduce simply the geodesic distance d between 2 points on the manifold, and it's just the length of the geodesic which is connecting those 2 points. And on the sphere, it's very intuitive. So on the sphere, the geodesic distance is, of course, the same as the great circle distance. And you can see that on the right side, this geodesic curve between the 2 points, P and Q. One thing maybe to add, the geodesic might between two certain points might not be uniquely defined, because you can see that, of course, also on the sphere, if you have the 2 points P and Q, which are the North Pole and the South Pole, then you have infinitely many geodesic curves between the North Pole and the South Pole. But the geodesic distance, of course, is uniquely defined, and it's always the same. Yeah, so that's it with respect to curves and distances on a manifold. And now after this, the very important key operator on these Riemannian manifolds are the exponential and the logarithm map. So these are really important manifold operators. So I will start with the exponential map, and yeah, actually I also when I got first into this topic, especially I needed some time to get the understanding of the exponential map. Yeah, and I will try to bring it as easy as possible. So you have now you have a certain reference point on the manifold, the reference point P. And you can see that on the upper right. And then you have a vector V on the tangent space of this point. So on the tangent space on the reference point, so TPM. Yeah, and then the vector V is now mapped to a point Q, which is now on the manifold, and to the point Q, which is reached after unit time, so t is 1, by the geodesic CT, which is starting at the reference point P, and which is going into the direction of the vector V on its tangent space. Yeah, so that's and this mapping now is called the exponential map. So it maps at a certain point P, and it maps now this vector on the tangent space to a point Q on the manifold. Yeah, that's it. Yeah, takes some time to grasp, but that's the easiest possible definition, I would say. Yeah, and the exponential map maps now the tangent space TPM to the manifold. Yeah, and you can see this here. So the mapping is really between the point V on the tangent space down to the respective point Q on the manifold. Yeah, and the logarithm map, of course, is the inverse. So as usually, so the mapping, the log P from Q, which is a point on the manifold, to the tangent space of P, is called the logarithm map at the same reference point P. And yeah, it's of course the inverse mapping to the exponential map. And it can be proven that it's locally defined, at least around the neighborhood of the reference point P. And yeah, it maps now the manifold to the tangent space at this reference point P. So it maps back, I would say, these points Q on the manifold to the vector V on the tangent space of this reference point P. So why are these operators so useful? So informally, you can say this exponential map and the logarithm map, these operators are able to move points back and forth between the manifold and the tangent space locally, and they are doing this in a distance preserving way. So you have the distance on the tangent space between P and V is the same as the geodesic distance between P and Q on the manifold. Yeah, so these are really the key operators. And then, of course, for deep learning and for neural network, you need also a sort of a convolution operator. So how can you define such a convolution operator on a manifold? Actually, on a manifold, there is not a unique way, but if you check out the literature, you can define it in a couple of ways, but there are two very popular ways to implement to define such a convolution on a manifold. The first one is you define the convolution via a weighted Frechet or Kacha mean. Sounds complicated, but actually it's just a generalization of the arithmetic mean to non-Euclidean spaces, to manifolds. Because this is the Frechet mean. When you look it up, it's just the point on the manifold which minimizes the weighted or unweighted squared sum of the distances to all points which go into this mean. And actually, the arithmetic mean, you can calculate it the same way as the minimum of the sum of the squared distances to all points which go into the arithmetic mean, but of course nobody does it that way. So it's just the natural generalization of the arithmetic mean. And then the other way is sort of, as a weighted sum in the tangent space. And this is shown in the bottom, and it's also very intuitive. So what is the procedure there? When you take a look, the first part is, of course, you're mapping everything, all points from the manifold onto the tangent space. So here you need, of course, the logarithm map as which I presented just before. And then you in the tangent space, of course, this is a normal vector space. So you can do here a normal weighted sum. And after that, you have the mean point as a vector in the tangent space. And then you're just projecting this mean vector in the tangent space down to the manifold, of course, via the exponential map. So these are the two possible generalizations. There is just one point. Of course, all these weights here, either with the Frechet mean or also in the tangent space, but especially in the Frechet mean, a weighted mean, of course, must have non-negative weighting factors. So there is sort of sort of a bit of a restriction. Of course, a convolution can have arbitrary, also negative weights. But I didn't find here some paper which allows this. Yeah, so that's it. Actually, I have also, I will tell that also later. I have actually a long version of this presentation. I had a tutorial, a longer one at the conference, and there I have also slides with other operators on the manifold. But I will refer to it because, of course, you need also not only convolution, you need like a batch normalization, you need like a nonlinear activation function and so And there are generalizations also of those operators to manifold. All right, so, and there are also all sort of differential operators on the manifold, which are also differential forms and so on. So all these, which are also useful for certain applications. Um, Then just one slide because I really like the connections between these, and because they are also important concepts or structures. So what is a Lie group and the Lie algebra? Sounds also difficult, is actually very simple if you had some basic algebra and also linear algebra. So a Lie group is now just a smooth manifold, which forms also a group. So you need now so the group in the algebraic sense is defined by the four group axioms, which I have here on the right side. So you have the closure, so the product, so-called product, I would say, on the group must be also an element of the group. Then you have to, of course, the associative, associ yeah, associative axiom. And then you have to have an identity element, which is usually named with I or E, and you have to have an inverse element for each element. So if you have this, then you have a group. For example, the rotation matrices, of course, they're building a group. Yeah, and both group operations, which are usually called multiplication and inverse, must be also smooth mappings of on this manifold. Yeah, so that's a Lie group, and the Lie algebra is now also very simple. Actually, a Lie algebra, which is a vector space. So this Lie algebra G of a Lie group M is now just defined as the tangent space TEM at the located at the identity element. That's it, more or less. Yeah, and E is the identity element of the group. So also actually sounds complicated, but quite easy actually to not to calculate, but to understand. Yeah, and some thing which might be a bit lead a bit to confusion is that these Lie groups, they provide also a sort of a natural exponential map, but this may differ from the exponential map defined for Riemannian manifolds. But then the nice thing is that at least for matrix Lie groups, it is identical to the normal matrix exponential operator. And also there is a theorem which follows from Peter Weld's theorem, which states that actually all compact Lie groups are matrix groups. So, and then you have the normal matrix exponential, which you can actually there are a lot of which can be computed actually in an efficient way in all numerical packages. Yeah, that's it more or less for the sort of theoretical part. Just also good to know is now that the common manifolds which are used in computer vision. So what are those commonly employed Riemannian manifolds? Of course, the n-dimensional sphere, Sn, is usually the short form of it. Then SON, the special orthogonal group, which is the Lie group of n-dimensional rotation matrices, um, usually in 3 or 2 dimensions. So n is usually 2 or 3. And then you have the special Euclidean group, SEN, which is also the Lie group of rigid body transformations. So as I said, transformation and rotation. And in matrix forms, you usually have these 4 times 4 homogeneous matrices. Yeah. Think like, for example, the transformation between two cameras which are viewing the scene. Then you have also important manifolds dealing with p-dimensional. So the set of all p-dimensional subspaces of Rn is called the Grassmann manifold. And it's also an important Riemannian manifold. It's useful also for sort of like dimension projecting to a low dimensional space and so on. And then you have this Stiefel manifold, which is also sort of related somehow to the Grassmann manifold, which is the set of all orthonormal p-frames of Rn. So sort of the p-dimensional orthogonal subspaces of Rn. And of course, the symmetric positive semi-definite matrices, they are also building a Riemannian manifold, which is usually the sign is Pm. And these SPD matrices, they are building sort of this positive semi-definite cone. All right, so now let's get practical. So I will show now applications of geometric deep learning, now also with graphs actually, in the multimedia, in the computer vision domain. It will be a very diverse mix. Yeah. So let's for similarity search and retrieval, I found a nice a nice approach by Isken et al. It's a little bit older, and it deals with identifying hard training examples, which is of course useful, for example, if you're doing some sort of a curriculum learning schedule where you're first training with the easy example and then you're getting progressively larger. Then you need to identify which one are the hard training examples. Of course, one proxy for that is always the loss, but they have really an elegant approach. They are identifying now the hard examples by comparing the distances or similarities to a certain reference point, I would say, measured via Euclidean distance and via geodesic distance on the sort of natural manifolds where these points, these samples are laying. You can see that on the right side. So you have here in black this sort of anchor point. And then in A, you have now the nearest neighbors uh, calculated with the Euclidean distance. And you see, you get there also points which are actually lying on the neighboring manifolds, and we don't want to get those. And in B, you see that the nearest neighbors, when you measure it with a manifold distance, with a geodesic distance on this natural manifold, then the nearest neighbor sort of is staying at the same manifold. Um, and now the hard positive and the hard negatives are actually the sort of the set difference of those two. So you can see the hard positives are identified as the points which are neighbors in the manifold with the manifold distance, but not neighbors when using the Euclidean distance. And the hard negatives in red, it's the opposite. So these are the neighbors which are identified, which are neighbors with the Euclidean distance, but not with the manifold distance. So really a clever thing. And what they are also doing, which is also, I saw that in a couple of papers, because often this geodesic distance is not so easy to compute. And you can compute this actually approximately by doing a random walk on the Euclidean nearest neighbor graph. And that's also a nice thing which works also for sort of complicated manifolds. All right, then a nice example for in the field of object detection and image classification is how to transfer a CNN which has been learned on normal photos from a certain to these 360 images. So transferred an existing CNN which has been trained on normal, let's call them perspective images, to now the spherical images, but we don't want to do an additional annotation or an additional training step. And we are this, they have now a sort of proposed a sort of, yeah, you can say it sort of imitation learning approach where they're mimicking the outputs from of the CNN model on the perspective images. And from that, they have from faster RCNN, they are getting a faster RCNN variant for the spherical images. Here you can see how such an equirectangular image captured from a 660 image typically looks like. And you can see immediately the problems, so the distortions towards the poles, and also, for example, on the right image, the dispersion detection sort of bounding box is shown, of course, on the left and right border, which is actually, as I said, as I told you, an artificial border. Yeah, then for image synthesis and enhancement, I found also a nice example for an algorithm for image editing by manipulation of the latent space manifolds. So it's an ACMM paper, a recent one. And the nice thing is that it can really perform highly realistic face manipulation tasks with minimal supervision. And the way it works is that it basically estimates linear directions in the latent space manifold of the style gun 2 network just by using a few images. So sort of a, maybe few-shot learning method. And it introduces also a novel and interesting method for sampling from this style manifold. And you can see the results here. So from the source image, you can modify the expression. Then you can modify also the pose of the face. You can make it older, and you can add glasses, or for example on the bottom with the guy you can add facial hairs or remove them and so on. So also a nice example really for geometric deep learning method. Yeah, skeleton-based human action recognition is a prime example for graph for for the usefulness of graph in neural networks. So actually, that's something I'm now working in a project, and when you check out the fast human record algorithms actually are doing first the pose estimation, and then they are doing such a graph using a graph neural network. And this is one of those. It's a geometry aware algorithm for this skeleton-based human action recognition. And the interesting thing is that they are modeling these skeleton sequences. So here, not as a graph, but as trajectories on the so-called candle shape space. And then they're feeding it into a sort of classical CNN LSTM network. The candle shape space is a manifold, a special one. It's actually quotient manifold, which is invariant against location, scaling, and rotation. And of course, this makes very much sense because these are transformations which do not change the shape of the of a certain, for example, of the skeleton. Um, I think I won't. Here is the overall workflow, but I won't go into details here. Then also for video analysis, there is a nice approach which is called DreamNet, Deep Riemannian Manifold Network for SPD matrix learning. So symmetric positive definite matrices are those. Yeah, and it proposes a full-blown neural network over the manifold of these SPD matrices as the backbones. So the input is a symmetric positive definite matrix. And then it sort of constructs a cascade of Riemannian autoencoder to it in order to enrich sort of make the information flow within the networks more natural. And the nice thing is that on diverse tasks like emotion recognition, also hand action recognition and human action recognition, they show a favorable performance. All right. Then also, of course, for 3D data processing, there are interesting geometric deep learning based approaches. And I found a nice approach. These authors are doing so-called unsupervised geometric disentanglement for surfaces via a CFAN variational autoencoder. So they propose an algorithm for geometric disentanglement, so sort of separating the intrinsic and the extrinsic geometry of 3D models. And these surface features now are modeled as a combination of these so-called conformal factors and of surface normal vectors. And so conformal factor is simply, it defines a conformal deformation, so an angle preserving deformation. And based on these features, they are proposing a convolutional mesh autoencoder, and they are showing that in a couple of 3D tasks like 3D surface generations, but also reconstruction and interpolation, they are showing that the approach is really state of the art. Yeah, then nonlinear dimension reduction. There, of course, you can also use this geometric deep learning algorithm. Actually, a couple of survey papers are um, um, as um, mm, making the term manifold learning equivalent to nonlinear dimension reduction. So if there is sort of like survey of manifold learning, but in my view, manifold learning is much more. So I don't agree to that. Yeah, so in nonlinear dimension reduction, of course, I suppose every one of you has already used like TSNE or a PCA. And they are proposing a nice algorithm for this task, which is called SpaceMap. And they introducing two really interesting components. The one is which they called equivalent extended distance, which makes it possible to match the capacity between two spaces of different dimensionality. And of course, that's what you're actually doing in nonlinear dimension reduction. And the other interesting component is which I called hierarchical manifold approximation. So you have here a manifold which models more or less the rough structure. And then you have submanifolds, which are more modeling the finer structure. So sort of, I don't know, multi-resolution or multi-scale manifold approximation, I would say. And on the right side, you can see here, yeah, sort of the classical dimension reduction algorithms and the result, like PCA, SNE, TSNE. UMAP is also very popular, and the most right is SpaceMap. And you can see, for example, when you look at this classical example, which is the spiral, that the space map is really able to flatten it out very nicely. Yeah. And then, of course, I have to promote also a bit of my work. But also because it's also really a big topic now, the topic of model merging. Sort of fusing together multiple fine-tuned models to get a better one. And there are a lot of papers here. And what I was working on is which I was calling the manifold mixing model subalgorithm. Um, and um, what it does is you can see it as a Frankenstein model actually. It fuses it generates a fused model from multiple fine-tuned models. And in sort not in sort of a local way. So what it does is it mixes together the latent space manifolds of these models MI in an optimal way. And the mixing factor I let these are the mixing factors are now calculated by a optimization step, and I'm using here gradient-free optimization with the Nevercard pattern package. I can really recommend this package also for things like hyperparameter optimizations and so on. And the nice thing is that this optimization is done on the original data set. But the model and it improves the model accuracy now on like a typical image classification task. It improves the model accuracy by like 0.5%, but the real change here, I would say, is that it improves the out of distribution accuracy by like 3.5%, which is really a thing, without ever having seen these out of distribution data sets. So with respect to the best fine-tuned model. Here on the chart, I was using like a clip model trained for image classification on ImageNet, of course. And here I measured the model accuracy. And for out of distribution accuracy, there are like 5 variants of ImageNet, like ImageNet A, which is sort of the difficult examples, which are um, which are which a simple image classification algorithm gets wrong, or you have ImageNet a sketch, where instead of the photo of a lemon, you have a black and white drawing of a lemon. You have ObjectNet and so on. So the really nice thing is that this model merging is really doing a good work in improving the out of distribution accuracy. So the generalization, I would say. And you can see this here on the right side. All these green points are all these multiple fine-tuned models. For example, when you're just training with different data augmentations, with different learning rates, and so on. And usually what you're doing is you're picking the one with the best validation accuracy, which would be this one. I think you can see the mouse pointer, or so the most right one of the green points. But this one is very is significantly worse than the merge model when on the out of distribution data sets. Yeah, and the star here is our merge model, and actually the uniform soup is also it's a simpler algorithm, and it's also doing very quite well in terms of generalization out of distribution performance. And it's super simple to calculate. You're just averaging all these green fine-tuned models. Yeah, greedy soup is a bit more involved, but not much more. And our algorithm is actually combining the performance, the good performance of greedy soup and uniform soup. Okay, just a few slides more, and then I'm done. Just to show you a bit the open source software packages for geometric deep learning. So for Riemannian manifolds, I found a few ones which are PyManopt, GeoOpt, GeoMstats, and Theseus. And then for graph neural networks, there's a nice library, so PyTorch Geometric or PyG. And for nonlinear dimension reduction, yeah, there are quite a few algorithms, and there's a package called Paradigm. And I will just go a bit briefly about GeoOpt, and the other packages are quite similar. So the nice thing is that it's compatible with PyTorch, so it uses the same tensor formats, autodiff, and so on. You have support for the commonly employed manifolds. Uh, the cool thing is it supports also the more exotic manifolds, like the Birkhoff polytope, which are the double stochastic matrices, or the Poincare ball, or the hyperbolide, the model which is sort of a yeah, space with a negative curvature, or so manifold with a negative curvature. And it provides also stochastic optimization algorithms which can be used on these manifolds. So, of course, the usual ones like SGD and also AIDA. And it provides also sampling from a probability distribution on the manifold, like Hamilton or gradient Langevins, Monte Carlo, and so on. Yeah, this is just one code example here where you're doing an optimization with Adam on the manifold of the double stochastic matrices, so on the Birkhoff polytope. Yeah, so that's it from my side. Just a few things. If you need the slides, you can contact me. I have also the slides of this longer tutorial where I have more information on more application examples and so on. And the reference of the form SU are actually referring to the respective reference in my survey paper. So I have here a short survey paper about manifold learning and its applications, which is also online available. That's it. So the research has been done, funded within the AI for Media project. So I'm sorry for overextending a bit my time slot, but I don't know. Do we still have time for questions
Well, maybe we
or
can get one or two questions if anybody is interested.
yeah?
So just to start up with, I'm just curious if you can comment a little bit on the limitation of using this, let's say the manifolds, right? Because the application seems to be quite exciting, but then why not everybody is using this manifold? So what are the down?
Yeah, the applications are usually these operators, like for example, the convolution, or even the convolution operator on a manifold, or even the simple things like the exponential and the logarithm map on the manifold. They are of course depends on the manifold you're using, but usually they are computationally significantly more expensive than the normal operations. Like for convolution, you have a super optimized CUDA kernels or CUDA kernels. I think that's the main thing, and the other thing it's maybe still a bit exotic, I would say, for many people, and you have to get into a bit into the topic. And I had also when I first started with that, I has had also so there is sort of a learning curve, yeah, um, to um, into all this material, yeah. I think these are the main reasons, yeah. So of
Hmm.
the more computationally expensive, and also you have to get the mindset, I would say, a bit.
Okay. Yes. I mean, it seems.
Yeah.
I'm just curious. One more thing is that how does this, let's say, manifold learning and manifold manipulation be used with, let's say, some recent generative methods like, I don't know, flow matching? Have you seen anything on this direction? Because also there
Um,
you are kind of looking into the latent space and you want to model the
yeah,
latent space as a manifold.
yeah. Yeah, I did the survey 1 year ago, and the research was done. So the paper is from 1 year ago, and the research was yeah, like over the year before that. So there are of course newer. So GAN is already old, of course. So as I saw, so like with nerves,
Mm-hmm.
um, I think I have run applications with nerves and manifolds, but I have it only in my long version or in the tutorial and also in the survey paper. And I suppose also now, like diffusion models, also there are approaches also which going into this, which employing concept from geometric deep learning. Yeah.
Okay.
And I saw recently also papers about hyperboloid um, neural networks, I think, which are also interesting. So I think it's getting a bit traction. Yeah.
Okay.
Yeah.
Anybody a question? If not, I think so. Okay. If not, let's thank Hannes for his interesting
Yeah.
tutorial, and
Yeah.
well, thanks a
Thank
lot
you.
everyone for being here. Okay. Have a good evening. Thanks a lot again, Hannes.
Yeah. Yeah. You're welcome. Thank
Thank
you.
you.
Bye.
Bye bye.